Good morning, afternoon, or evening, whatever the case may be. I'm Paul Beckwith. I'm with the University of Ottawa, Laboratory for Paleoclimatology, also with Carleton University, Department of Geography and Environmental Studies. Today I'm going to talk about methane, specifically methane that is coming up from the seafloor sediments on the eastern Siberian Arctic Shelf. Recently, a friend of mine, Nick Breeze, who has this website Envisionation, did an interview with Natalia Shikova and Igor Samilitov on the Eastern Siberian Arctic Shelf work that they've done, and they published a paper recently. So I'll get right to it. In this particular video, I'm going to concentrate more on the interview by Nick Breeze. So we're talking about subsea permafrost on the East Siberian Arctic Shelf, and it's in accelerated decline. So this paper that just came out is in Nature Communications Journal. It's open access, open source, so you can see the paper here. Now, notice it was first received July 2016, accepted May this year, published 22nd of June. It took almost a full year to get published. Now, this has to be in the scientific literature for 2 years before it's even considered by the IPCC. So that would be June of 2019. I don't know when the next IPCC AR6 is going to come out, but AR5 came out in 2013. So if this one's in 2020, the next one, this paper probably won't even make it into there, which is why the IPCC process is flawed. We need to have updates every year on what is going on. So getting back to this paper, it shows mechanisms for the destabilization of subsea permafrost. So it provides insights into increased emissions from this shelf. The Eastern Siberian Arctic Shelf, ESAS, has the world's largest deposits of methane. Now, the permafrost that's embedded in the seafloor has acted as a seal for thousands of years, restricting the flow of gas like methane through the sediments into the water column into the atmosphere. But the permafrost is degrading, and there's gas migration pathways that are occurring and resulting in the emissions that we're seeing. So in order to predict climate change, and specifically temperatures in the Arctic, we need to know near future methane releases. How much methane is coming out? Okay, so the decay, what the paper is showing significantly is even permafrost that was only that was only submerged relatively recently, less than 1,000 years ago, is currently thawing and releasing methane. And there's no force that we know of that can stop this trend of further decay and increased emissions as the Arctic continues to warm. So this is the North Pole. This is looking down. This is a polar view from the Russian side. Okay, Greenland's up here. So this is the Eastern Siberian Arctic Shelf, the East Siberian Sea, the Chukchi Sea, and let's have another couple views of this. So if you Google polar data, okay, this is an interesting website here, just polar data. Okay, all these different maps of the Arctic, okay, showing various things. This is the bathymetry, different navigation pathways, etc. And this is interesting. This is showing the forming of snow cover on the land, and then the loss of snow cover and the greening of the vegetation on a yearly basis, going through time. But this is what I want to focus on here. This is the Eastern Siberian Arctic Shelf. Average depth about 50 meters, and then so there's these continental shelves all around the Arctic. And if we go down, this is the circulation patterns of the water. So you can see things like the Beaufort Gyre, transpolar drift, and then the ocean currents carrying warm water that come in underneath the ice. and that'll be very important. There's lots of other interesting maps on here. This is the seafloor features map, the bathymetry. So what you can see again is the eastern Siberian Arctic Shelf, and there's many other continental shelves. Okay, so this is the area that we're focusing on. So just to give you an idea of the size, I want to show you, this is the seasonal variation of the Arctic sea ice extent. So it maxes out at about 15 million square kilometers, and the minimum, the new record in 2012 was just over 3 million square kilometers. Okay, so keep those numbers in mind. That's sort of the range. The previous record before 2012 was 2016 and 2007, and that was more like 4 million square kilometers. Okay, so how big is this shelf? It's the largest and shallowest shelf. Mean depth of 50 meters. The area is 2 million square kilometers. Okay, so this is a large area compared to the total area of the Arctic. So the seabed has frozen organic matter, basically subsea permafrost. Permafrost is ground that remains less than or equal to 0 degrees Celsius for 2 or more years. Okay, so why is it there? It started developing when the northern hemisphere cooled around 2.5 million years ago. So it was above sea level. The atmosphere got very, very cold. So that there was a lot of water turned into ice, which went on continents. So sea levels dropped. So this area was 50 meters below the sea now today, but it was much, much higher than the sea level back then for a long period of time. So the permafrost was formed. Eventually, as the glaciers melted, sea level rose, submerging the permafrost. So that goes, the inundation of the shelf with seawater, it changed the properties because it increased the temperature as much as 17 degrees Celsius. Okay, so you have seawater just above freezing, covering the permafrost, versus the temperatures of the permafrost before, which were about minus 17 or colder degrees Celsius. Now, the last interglacial peaked about 21,000 years ago, and after that ice started melting. At that point, at the peak of the last interglacial, the last glacial maximum, the LGM, the last glacial maximum was about 21,000 years ago. Sea levels were 120 to 130 meters lower than today. So this shelf, with an average depth now of 50 meters, had an average elevation above sea level of 70 to 80 meters. So it was very cold, and the permafrost was strengthened. And then the entire shelf area, the sea level started rising up, and there were numerous thaw lakes on the terrain, underlain by talax, which is unfrozen permafrost. Okay, so let me just have a look here. Okay, so this is to give you an idea. This is what the methane clathrates look like. You've got water molecules that are frozen around a methane molecule. When and this stuff will be stable when the pressure is high enough and the temperature is low enough. When you raise the temperature or relieve the pressure, the ice around starts melting. The whole structure expands 160 times roughly, and you get methane gas. Okay, so this is down here in these clathrate mounds on the seafloor. There's methane seeps, and there's clathrates up here, and so on. Okay, so why does this stuff form, these methane clathrates? Well, on the land, okay, there's a geothermal gradient. You get heat from the earth, so it's hotter as you're deeper. And that as you get closer to the surface in the Arctic, the temperature goes closer and closer to the air temperature, and there's a hydrate gas phase boundary. So all this area in between is where you can have methane hydrate being in stable form. This is permafrost on ground. So take the permafrost on ground and suddenly inundate it with water above, and you have all of this hydrate here, which is not very far down under the water. Okay, if you, in the ocean here, you know, if the ocean floor is 1,200 meters deep, then this is the water temperature, the red line. This is a hydrate gas boundary. And so the hydrates would only be, of course, they can't be existing free floating. They're buoyant. They would rise to the top. So in the seafloor, you get these hydrates here. This is the geothermal gradient. So it's too hot down below them. Above them, it's cold enough. So you get the hydrates in this region. So if you track this temperature curve and the gas phase curve, you come here. They meet here, which is, call it, it's about 280 meter water depth, or 300 meters, call it. So at 300 meters of water depth, the pressure and temperature in the ocean is sufficient to have hydrates on the seafloor. Okay, not in the sediments, but sitting on the seafloor. So let's have a look now how that relates to the Eastern Siberian Arctic Shelf. Okay, so basically the Eastern Siberian Arctic Shelf, the analogy is it's like a bottle of champagne with a cork bottle. Okay, there's gases that are in the sediment, but as long as you have a cork on the bottle, or as long as you have permafrost in the sediments and the gas is confined, it keeps accumulating, the pressure rises, but the cork or the subsea permafrost is a lid, and it keeps the methane in the shelf. It was thought that that lid would be stable for a long period of time. Okay, just before it was permafrost on land, and then it was submerged. Now it becomes subsea permafrost, and there's an impermeable lid. There's nothing to worry about. Okay, but when that lid starts losing its stability, when it starts to thaw, then the methane can be released. And the amounts of methane that are currently being released make us think that the permafrost is disintegrating, and that paper, which I'll talk about in a separate video, talks about the rates of degradation of the permafrost over time. Now, the thing is the paper looked at it over a 30-year time period because there were some drill cores from the early 80s. So what question Nick was asking is, okay, it's 3 decades, you know, how are these changes conclusive? So the thing is there's, as soon as the continental shelf was inundated with water, seawater, that brought the temperature up about 17 degrees Celsius and started the natural warming of the subsea permafrost. But of course, and that started, say, 5,000 years ago, when the sea level was high enough to overcome to cover the Eastern Siberian Arctic Shelf coast. So the permafrost started degrading, but you know, many scientists suggested that it would keep its integrity for millennia. But areas that are near the coastline that were only submerged in less than 1,000 years ago are releasing hydrates and releasing methane. So this means that the permafrost has thawed already in those regions, which is much less than this 1,000 years. So we have to add the natural warming to the anthropogenic warming, and together they're accelerating the pace of natural processes. Okay, so we need to talk, okay, so the interglacials are periods between ice ages, and the permafrost starts to thin due to the warming. Okay, but in previous interglacials, like the Eemian, for example, the temperature was higher, and the methane hydrates were not all released, that should say. I mean, some of them would be released if they were up closer to the surface, but lots of them were not released. And the thing is that in the Eemian, 130,000 to 115,000 years ago, temperatures were higher, you know, but the duration during which they were higher was short, about 2,000 years. And then there was cooling. In the Holocene, it's been 5,000 years of warming since the inundation has covered the shelf. So I'm going to have to stop here and continue this in a second part video. Thank you for listening. Good evening, or afternoon, or morning, whatever the case may be. I'm Paul Beckwith with the University of Ottawa and also with Carleton University, teaching many courses, mostly at Ottawa U, but more recently at Carleton. So I'm going to continue this a previous video where I talked about what's happening on the Eastern Siberian Arctic Shelf in terms of methane, what the latest science from a paper that was just released within the last few days has been saying about the methane emissions from the shelf and the structure of the permafrost in the shelf. So for subsea permafrost, it was long thought that the duration of warming is more important than the surface temperatures themselves. Because in order to start thawing, you have to reach an equilibrium temperature where the external environmental temperature that heat transfers into the permafrost and thaws the permafrost. So as long as the temperature is above the thaw point, about 0 degrees of the permafrost, and the stuff will thaw. Once it's thawed, it's no longer permafrost. Bacteria can start decomposing the organic matter, which they can't do when it's in frozen state. And if there's no oxygen available, it produces methane through anaerobic decomposition. So computer models have looked at how long it would take heat to transfer through the different layers of permafrost, and they come up with numbers like hundreds of years or thousands of years. But what we're seeing, the observations we're seeing this happening now in the Arctic in front of our very eyes. So these models are once again not they're just not sufficient to explain what is happening in reality. There's gas migration pathways that are providing migration, providing pathways for the gas to bubble up and come out. So what's important is the thaw point and how long the warming has lasted. Okay, so as the longer the duration of the warmer period, the thinner the subsea permafrost, and therefore the unfrozen regions can lead to gas migration pathways, letting the methane come up. So in many places, the permafrost has reached that thaw point. In other areas, it hasn't reached it, it's getting close. So we need to really, if it's not reached, we can get linear emissions. Okay, slightly warmer temperature, smaller linear amounts of methane are coming up. But as you get these weak points in the sediment, those linear trends can quickly become exponential. And the point here is it's a fine line between those two states. Okay, so they use the expression turning point, or you can say a threshold, or you can say a tipping point, or you can say an abrupt change where the linear change actually becomes exponential. And we're seeing that in all kinds of different metrics in the climate system. Okay, so when we talk about linear changes, you know, those changes can be slow over long periods of time. When we're talking about exponential changes, every single year matters. There's a huge difference. Okay, so the whole Eastern Siberian Arctic Shelf is about 2 million square kilometers. So Shakova and Samilitov estimate that about 10% of that, 200,000 square kilometers, have what are called hotspots within them, areas where methane is observed as being far greater than a low background area. Okay, so is a sudden burst of methane feasible? This was a burst of 50 gigatons was modeled by Wadhams in, I believe, 2013 in a paper that he did with an economist, and they found that would cause an impact to the global economy of about $70 trillion. So let's have a look. Well, what is the background? The background is something on the order of 3 milligrams of methane being released per square meter per day. Okay? That's in the background area. That's in 90% of the Eastern Siberian Arctic Shelf. What we're seeing in these hot zones or hot spots are up to 3 kilograms, 3,000 grams per square meter per day. Okay, so if you take the ratio, 3,000 grams to 3 milligrams, which is 3/1000ths of a gram, the ratio is 10 to the cube times 10 to the cubed, or 10 to the 6. It's 6 orders of magnitude. Now there's some variation in these numbers, so the paper is arguing 3 to 5 orders of magnitude change, a difference between them. So in other words, in the hotspots, or the hot zones on 10% of the continental shelf, we have very large amounts of methane coming up. And this is the difference between linear and exponential. Okay, if the hotspot area doubled, there'd be a huge difference in emissions. Okay, or 3 times, an even bigger difference. Also, you know, could there be a gigaton release? She said she doesn't know, but she can't exclude this scenario. What would be the argument to exclude this scenario? Okay, I mean, 5 orders of magnitude difference. You know, this is this is a huge factor difference. So also, as gases are bubbling up through the unfrozen regions, they mix sediments and take things with them. The hole can be larger and larger and larger. The gas migration pathways will grow. So not only will the area of hotspots grow, but the size of the migration pathways grows. So we get exponential growth. Okay. Now the thing is it's not just methane in the form of hydrates. There's lots of methane in the form of free gas, especially below the hydrate stability zone, which is only a couple hundred meters thick. So this free gas has accumulated for hundreds of thousands, even a million years. So there's huge amounts of this gas, and it's at high pressure, so it goes up through those weak spots just as much as the thawing hydrates. So this could allow a large release, you know, an outburst, a bomb, whatever you want to call it, a methane clathrate gun. So, you know, a lot of the more we find out about this system, the more worrying it looks. This is why, you know, it's very easy to argue at this stage that we're in a climate change emergency. So how do we know these hydrates are there? Well, they're just drilling in and they're finding them there. Okay? The hydrates are only one form of possible reservoir. Okay? The methane that is in gaseous form is huge compared to what's just in the hydrates. The hydrate layers are a few hundred meters and are therefore a very small fraction compared to the thousands of meters of underlying gas-charged sediments. Okay, so how much methane's in the atmosphere right now? Okay, there's 5 billion tons of methane in the Earth's atmosphere right now. 5 gigatons. That's about 1% of the frozen methane hydrate store in the East Siberian Arctic Shelf. So if 1% is released, that would double the level of methane in the atmosphere. But the hydrate pool is only a small fraction of the total methane. Okay, the depth of okay, so there's a sedimentary drape. There's sedimentary rock which goes down. It's a few kilometers in places, up to 20 kilometers deep in places. So that's just rock. It doesn't contain gas or methane, at least not significant amounts, it's believed. So it's the sediments that are lying above that contain the gas. So it doesn't make any difference if the gas coming up is from the hydrates or the free gas deposits. The pressure is high. If there's a pathway, if the cork is off the bottle, it can come up. It's ready to go. So now this says the estimated amount of hydrates is 1,500 gigatons. So if 1% of that would be 15 gigatons, and that's 3 times what's in the present atmosphere. So not sure how that number is different, because I thought 1% would release 5 gigatons and not 15 gigatons. So there's a bit of ambiguity there, which needs to be clarified. The hydrates are there. Okay, there's been a lot of disbelief from scientists because you know, the depth is only 50 meters of water over that shelf. But South Korean expedition measured and sampled these hydrates recently. They're going to publish the data soon. Okay, so observations show that the hydrates are there, and the recent paper shows that the gas front is propagating in the sediment. So in other words, the permafrost is not, that's closer to the surface is thawing, and the thaw line is going deeper and deeper. So how do we know that okay, so how do we know that there's hydrates? Why should there be hydrates existing there? Okay, well, we've already, from this curve, if you just have seawater, you can go down about 300 meters and you can get hydrate formation on the surface of the seafloor. Now, the eastern Siberian Arctic Shelf is 50 meters deep, so we got to account for another 250 meters of water. Okay, the density, so we need to look at the density of materials. Density of water, 1 gram per cubic centimeter. The density of many sediments, of many rocks and things on continental shelves is about 2.7, up to 2.7 grams per cubic centimeter. The density of rock on the seafloor, about 3. It's about 3, up to 3. It's about 3 times higher than water. So in order to account for 250 meters of water, right? We've got 50 meters of water on the shelf. We need to account for 250 more meters of water. Divide by 3 by the density ratio. That's about 80 to 85 meters or so. So if you go down 50 meters in the water column to the seafloor, and then you go down about 85 meters in the sediments, then the pressure will be sufficient to form hydrates. That's if it's all, the sediments are all a density of 3. Usually there's pores and there's water in those and there's gaps, so it's less than 3, so you might have to go down 100 meters or 150 meters in the sediments to get the pressure. But it's certainly, that's the mechanism, that's the physics of what's going on in that region. Okay, so let's go back here. So, okay, the other thing that I would like to point out is I'm going to talk about the features of, when a glacier covers an area and then it leaves. There's certain features that are on the land. There's certain, the ground can freeze because it's exposed to the air. You get the permafrost frozen, but you have areas, you have lakes and things. And so these lakes in this so-called thermokarst region can look like this, right? You get all these different pockmarked lakes, and if you go and look at the detail of the lake, then underneath the lake, there's a thaw region. If this is all permafrost all around, this whole region was originally permafrost, the lake is there, the area underneath gets thawed out, and this is called a talus, okay? Areas of unfrozen ground. So what happens when we inundate this whole thing? Sea level rises, we inundate this thing with seawater. Okay, it has been thought that the seawater near it can be near minus 1.8 degrees Celsius before it freezes, goes down, percolates through, and freezes this talus to make it to make the cork, give the cork, if you like, integrity so that methane can't come up through. But that is not so clearly happening now. So let's go over to here and see what happens. So here's, okay, so this is taking a little bit longer to explain. I'm probably going to extend to a third video so I don't have to rush too much. I try to keep these videos to about 15-minute segments because I find, that's sort of an optimal time. TED Talks are 18 minutes. These videos are 15. If it keeps me from trying, it keeps me on point. So let's have a look. So here we have a schematic of going through depth. We have 50 meters of water here, and we're going down in the sediments. And this is, I'm going to go through the sequence of this in the next video. So thank you for listening. Hi, Paul Beckwith, University of Ottawa and Carleton University. So I want to spend a bit of time explaining this diagram. This is a diagram. It shows the formation of different types of hydrate deposits in permafrost and their interaction with seawater on the eastern Siberian Arctic Shelf. So let's start with a warm period. We've got 50 meters of seawater. We've got 600 meters is the total depth from the surface of the water. And we have sediments here, and there's gas in those sediments. There's water, and there's gas in the pores of those sediments. There's a lot of organic matter in here that has been laid down over long periods of time from dying vegetation, plant matter, animals and plants that are dead, and also excrement from animals and so on. So there's lots of organic matter. There's lack of oxygen, so it's broken down and it can produce methane, and it can be in these sediments at various levels. Then we get a cold epoch. Okay, so the Earth is a lot cooler. So what happens is the sea levels drop because there's a lot of snow. For example, on Greenland and Antarctica, that snow eventually freezes into ice, and the ice builds up on the continents, and there's less and less water in the ocean, and the sea level drops. In fact, the last glacial maximum 21,000 years ago, sea levels were 130 meters lower than today, so that would take us down to sea levels being about here, okay? So, or even further down. So what happens is, in a cold epoch, the ground is very cold, you start getting it thawing, and the thaw goes deeper and deeper and deeper. So you have these permafrost boundaries here, you know, permafrost from the top, going down to this far. What limits it is there's geothermal heat from the Earth that is coming up, and that that prevents formation of permafrost further down. So you get a region in which the permafrost sits. You have things like salt diffusion going down to this region here. You also have this region here of these stars, crosses. This is a hydrate stability zone. This is where the pressure and temperature is sufficient so that that water lattice can form around the methane molecules and exist in a stable state. And below that, you still have the sediments that contain the gas. It's too hard, it's too warm. The geothermal heat makes sure that it's not frozen ground in that location. Okay, then along comes a warm epoch. Okay, the glaciers on land melt, the sea level rises up. We go up to 50 meters here in this example. And what happens is the heat from the water starts diffusing downward. Okay, and what we get here is we get thawing of the permafrost down to here by example. So this is still permafrost. This is still the gas in the sediment. But in this region, the permafrost thaws. You get decomposition, anaerobic decomposition by bacteria of organic material that produces the gas. Okay, the gas here. And this is a hydrate that is metastable. Okay, so it's not really, it's not that stable. You know, it takes time though for it to start thawing out. So it's thawing slowly. You know, as the duration of the warm epoch continues, this starts converting, these hydrates get converted to free gas, and the layer of the frozen permafrost drops even further. Even more time passes, and you start getting perforations of this layer. So you no longer have the cork is now broken. You're letting the genie out of the bottle. This free gas down here has open pathway to go up through the sediment and then go up through the water column and enter the atmosphere. The warming today is extremely fast. We had warming as we left the last glacial maximum. We've got huge amounts of human-caused anthropogenic warming. So we're getting very, very rapid changes and thawing of the permafrost, subsea permafrost, as shown in the Shkova-Samilatov paper. Okay, so what we're seeing is that this zone here of where permafrost exists is going deeper and deeper, about 6 inches per year. That's happened over the last 30 years. Okay, so we're talking about 15 feet or so of drop in 30 years. This is a significant amount of methane in those regions, and the rate is increasing of the dropping, and we're getting the perforation. And this is happening on about 10% of the eastern Siberian Arctic Shelf, which is about 200,000 square kilometers, rather, because the whole shelf is about 2 million. Okay, so this is a very significant effect. Okay, you know, why do some scientists say there could be no hydrates? Well, I mentioned this already. The argument was that the pressure wasn't large enough with 50 meters of water. The hydrostatic pressure, you know, for every 10 meters, it's about an atmosphere of pressure. So 50 meters of water is 5 atmospheres. Add 1 from the atmosphere itself, 6 atmosphere gauge pressure, or not gauge pressure, but absolute pressure. And then when you add the depths through the sediment, I said about 80 meters, 85 meters, if there was very little waters in the pores, if it was mostly compressed sediment. But, you know, because there's water and there's pores, maybe 100 meter, 150 meters in the sediment, and you get a high enough pressure that you get hydrate stability. Okay? So, because hydrates are associated with permafrost, their top boundary could be well below the seafloor, in fact, closer to the bottom of the permafrost, which it is if we've seen this. So, you know, this is just saying that because the sediments are denser than the water itself, you don't need as thick a layer. So instead of 1 atmosphere of pressure being from 10 meters of water, you only need about 5 to 8 meters of sediment, is said, to create 1 atmosphere of pressure. So, so this would be, you know, if the sediment had no water and was solid sediment and, you know, had the density of the 3 grams per cc compared to 1 for water, you'd only need about 3.3. But because there's pores and stuff, you know, 5 to 8. Okay, so the top boundary of the hydrate stability zone can be tens to 100 of meters below the seafloor. So it definitely exists there. Now also, when the sea was lower and the ground was cooling quickly, in the presence of water, there'd be expansion of the water in the ground, and this would raise the pressure. So this would cause high interpore pressures. So this means that the pressure is generated internally from these mechanisms during cold periods when the ground is freezing rapidly. So this means the upper boundary of the hydrate stability zone could occur in even shallower depths of less than 100 meters in the sediments. Okay, and also, also, you know, a major fraction of these hydrates form when the shelf is dry. So then we have this type of situation. You know, instead of the ocean situation, we have the permafrost situation on land. So we get these hydrates forming much closer to the surface. Suddenly we inundate with seawater, and these lakes and the thermokarst with the talics underneath get inundated, but then the methane hydrates are just below. Okay, so the problem is that, you know, up to now, once again, these models are really killing us. Everything's happening faster than expected in climate change because we have had a blind faith in models. We spent lots of money, lots of people, lots of resources, lots of supercomputers to crank out results from models, and though it's gotten ridiculous where the models are actually believed more than the actual data that is measured on the ground. And this is completely absurd and ridiculous. Okay, so here's a question. Could the 10% area of hotspots be very significant in releasing methane? Well, the answer is yes, right? The emissions are happening now as a result of the effect of natural warming over the last, since the shelf has been covered with water for the last 5,000 years, and anthropogenic warming, more recent warming, especially since 1750. Now, the problem is once the cork is removed from the bottle, how do we ever put the cork back in the bottle? There's no mechanism to stop the permafrost disintegration, right? We can't lower the sea level and freeze the stuff, you know, have the shelf above sea level and then freeze the stuff. We can't do things like that. So the problem is that once the cork is off the bottle in different regions of the, you know, think of it as billions of corks on billions of bottles on the eastern Siberian Arctic Shelf. On 10% of that area, we started taking corks out. So if we were to cool the Arctic, we'd still have methane coming up through the corks that have already been removed, but hopefully we wouldn't have additional corks being removed. So it is very, very crucial that we treat climate change as an emergency and we cool the Arctic to keep the methane coming up. We're talking about gas that's been accumulating for millions of years. The potential of the amount of gas is enormous. It will alter the climate and our planet drastically. So it's very vital that so this is a very, very important and key interview. You know, kudos to Nick Breeze for, you know, for taking the time and meeting and doing these interviews and posting them, because this paper, like I say, is you know, this paper is crucial. Now this paper gets quite technical, but I'm going to give a stab at explaining what I can from this paper in a future video. So I'd like to point out that I generate and do all this work on these videos on my own time. I don't get paid for it. This is why I ask people for donations to support my work, to support my ongoing research on these topics and videos, to try to explain, you know, how our climate system is changing much faster than people expect. So please have a look at other videos that I've done. There's many. Just Google Paul Beckwith YouTube Paul Beckwith, and you can find all of the videos on all these different topics. I should do a summary of all the different topics I've covered so it's easier to access through them. But if there's a particular topic like methane or temperature or whatever topic it is, if you Google YouTube Paul Beckwith in the topic, you can find videos on it. And I also, there's posts to my website, paulbeckwith.net, and there's a donate button there. So please support me with a small financial donation so that I can continue these videos. It turns out, as of now, I don't have a teaching position in either the fall or in the spring of next year. So this is going to be a bit of a problem for me. I was fully expecting to get something, and I haven't as of yet, and I'm not sure why, but that's the way it goes. So I do really rely on your support for doing my work. So thank you for listening.